So this morning I wanted to talk about chemical shift in NMR spectroscopy, and this is really what makes it a useful technique to us, and why the physicists, when they initially sought to study magnetic resonance of protons, decided, oh, it's not very interesting because they don't all appear at the same frequency in the same magnetic field. It depends on their chemical environment. And of course, that's what makes it useful to organic chemists, is that the chemical environment is reflected by the resonance frequency. And then as well, you get information from spin-spin coupling. So for chemical shift, I just want to introduce the concept and say, let's take tetramethylsilane as an example. Tetramethylsilane is a common NMR standard. And at a 70,500 Gauss magnet, it would resonate. You would flip the spin of the protons, and then you would have precession at 300 megahertz. So I'll write that as 300 million hertz. But this frequency, as we discussed before, depends on the applied magnetic field, B0, because the energy gap between the alpha and beta state and the rate of precession depends on the magnetic field. So at 117,500 Gauss, that frequency now becomes 500 million hertz, 500 megahertz. And this is why we call an NMR spectrometer with a 70,500 Gauss magnet a 300 megahertz NMR, and an NMR spectrometer with a 117,500 hertz Gauss magnet, a 500 megahertz NMR. And remember, the carbon frequency is very different. So here we're at 75 megahertz for carbon 13 NMR, whereas here we're at 125.6 or so, 125.7 megahertz. Now, for a plain vanilla methyl group, so just like the end of an alkane chain, for a plain vanilla methyl group, that frequency is going to be different than tetramethylsilane. In tetramethylsilane, the silicon is electron donating, and so you have extra electron density around the hydrogens, around the protons. So we're going to be about 300 million, 300 hertz, really more like 270, but I want to keep the numbers simple here. And on the higher field magnet, we're going to be at about 500 million, 500 hertz. And again, if I were being a little more honest, I'd say 500 million, 450 hertz. But I want to keep the numbers simple and round here. So rather than saying, okay, it's 300 hertz relative to TMS on this instrument, and it's 500 hertz relative to TMS on this instrument, we just take a proportionality or a quotient and say this is 1 part in a million. 300 is 1 part in a million here. 500 is 1 part in a million here. So both of these are at 1 ppm, which of course is the unit that is used. If we, just to give an example, I'll take a methyl group on a sulfur, I'll take methane thiol. If we go ahead and say that's going to be at about 300 million, 600 hertz, which is about 2 ppm, we can easily say, okay, it's going to be the same thing here. It's going to be 2 ppm on the higher field magnet. And so that's going to be 500 million 1000 Hertz. Now, immediately, I want to point out one point, although we're not going to be talking about spin-spin coupling today. I want to point out that spin-spin coupling is invariant in Hertz. In other words, coupling constant but the chemical shift is invariant in ppm. And the reason for this is spin-spin coupling is how the nuclei feel the other nuclei spin, mediated by the electrons of the bond, whereas the chemical shift is how the nuclei feel the magnetic environment that they are in, shielded or deshielded, or shielded by the electron cloud that surrounds them. In other words, the electrons surrounding the methyls here protect it from the applied magnetic field more than the electrons surrounding the methyl hydrogens over here in methane thiol. So, questions or thoughts at this point? So I want to go on then and start to talk about some factors that affect chemical shift. And our goal for today's lecture is really to come up with a mental calibration to be able to know where protons appear. There are tools, and I will introduce those today as well, to help you, or at least one of those to help you, but nothing replaces the ability to intuitively know where different protons show up. It assures you that when you draw a molecule out, you see, look at a spectrum and you think of a structure, you can quickly and critically say, oh, wait a second, no, it can't be that structure, because an ethyl group next to a ketone would have its CH2 at about 2.4 parts per million, but the CH2 here is at 4.1 parts per million. It must be an ethyl ester group. This is essential that you're internally calibrated in this. In a way, you can say that what we're going to do today is learn to read, or at least learn some basics. And of course, when you're reading, maybe in a foreign language, if you're just learning, you won't know all the words. But if you've got a good grasp of the basic words and the basic grammar, you can look it up when you encounter a word that you don't know, or at least you might have some idea if you're trying to make your way through French or Spanish or German, what that word might be, but you can look it up, but you know the basics of the context, and that's going to be critical. So one of the big factors that affects chemical shift is the shielding or deshielding environment, and a big factor then becomes electronegativity. So I'll start with methyl halides. I'll start with methyl iodide, methyl bromide, methyl chloride, and methyl fluoride, fluoromethane, chloromethane, and so forth. And we're going to look at the halogen series. Of course, the periodic table, we go down from fluorine to chlorine to bromine and iodine. The electronegativity, of course, goes in the opposite direction. But let's start with our chemical shift in ppm. So methyl iodide is about 2.10 ppm. Methyl bromide is about 2.70 ppm. Methyl chloride's about 3.05. Methyl fluoride's about 4.30. And you see that these numbers then go in an increasing scale that goes with the increase in electronegativity. Even if you don't remember all your electronegativities, you probably remember that fluorine is the most electronegative element in the periodic table. The Pauling electronegativity, I think most people for fluorine remember that it's 4.0. You might remember that chlorine's 3.0. You might remember that bromine is a little bit less, 2.8, and iodine is still less than that at 2.4. And so basically the fluorine is pulling the electron density away from the methyl group. We would say it is de-shielding it. So more electronegative. Leads to less electron density around the hydrogen. So more, I'll write this maybe as a little bit more complete phrase, more electronegative substituent leads to less electron density around the hydrogens. The inductive effect pulls electron density away. And that leads to the hydrogens being de-shielded, which we call downfield relative to the other end of the spectrum. So in other words, if you have a spectrum and you go from, say, 0 to 10 ppm, this direction is downfield. This direction is upfield. So usually you'll hear me referring to the downfield region of the spectrum, and I'll sort of refer over here or the upfield region, but it's also a term of relativity. The methyl group in methyl bromide is more downfield than the methyl group in methyl iodide. Now, it is really useful to have some calibration points in your head and to start to see trends. And so if you go ahead and let's go ahead and start with methane. Methane, oh, by the way, the symbol delta is another way of saying chemical shift. So the methyl group of methane, or methane itself, appears at delta chemical shift 0.23. And we already said that methyl chloride, chloromethane, appears at 3.05. Now, if we bring in a second methyl group, and this is where you can cultivate your intuition. So one methyl group's pulled away electron density a good bit. It's brought us from 0.23 to 3.05. If we add another, did I say methyl group? One chlorine. If we add another chlorine, it's going to pull more electron density away, but there's less to give. So you're going to move downfield, but here we move downfield by about 2.8 ppm. We're going to move downfield still a good bit more. Now we're going to be at 5.32 ppm. So another couple of ppm downfield, another 2.2 ppm downfield. If we go to chloroform, you probably already know that chloroform appears at 7.26. So we've moved another just about 2 ppm downfield as you've started to pull more and more electron density away. This is incredibly useful because you can start to see that to a first order approximation, the effects are almost additive. And we're going to use that first to calibrate our own intuition, to be able to see the effects of substituents. And then I'll show you how chemical shift calculators use these empirical additivity rules to go ahead and come up with estimates of chemical shift. Now, I find it incredibly useful to have a reference frame. That way you don't have to keep too many numbers in your head. You certainly want to keep some numbers in your head. But let's start with a reference frame, and I'll show you how that can triple your knowledge. All right, so let us suppose, at least for me, for my reference frame, I'll take a plain vanilla methyl group, and I told you before I was sort of lying by saying 1 ppm. It's more like 0.9 ppm, hence my asides on 270 rather than 300 and 450 rather than 500. A plain vanilla methylene group, RCH2R, no electronegative substituents, typically at about 1.3 to 1.5 ppm. In other words, this difference is about 0.4 ppm. And if we go to a plain vanilla methine group, I'll just write that as R3CH. Now we're somewhere around 1.5 to 2.0 ppm. And so, in other words, about another 0.5 ppm. Why is this useful? Because if you know the position of a methyl group, say next to a ketone, you can immediately intuit that, oh, a methylene group next to a ketone is going to be about 0.4 of a part per million more downfield. And a methine group next to a ketone is going to be a total of about 0.9 ppm more downfield. In other words, if a methyl group next to a ketone is about 2.0 or 2.1, a methylene group next to a ketone is going to be about 2.4 or 2.5. A methine group next to a ketone is going to be about 2.9 or 3. And don't lose the forest from the trees, because 2, 2.5, and 3 are significantly different numbers. You don't need to worry about the very last digit, the 100th place. You're not going to be able to estimate that, that exactly. And indeed, it's going to depend a little bit on solvent and other effects, as well as more remote substituents in the molecule. But the big picture of 0.5 ppm or 1 ppm, you should be able to get. So if a methyl group next to a chlorine is 3.05, what would our estimation for the chemical shift of ethyl chloride be? What would you estimate for that?
3.50.
Pardon?
3.50.
3.50. So we'd estimate 3.5, and the actual is 3.47. Spot on. And, you know, this last decimal place is going to change if you're in deuterobenzene or deuteroDMSO or deuterochloroform, but you're going to know what you're looking for. And what would we estimate for isopropyl chloride then?
Roughly 3.9 or 4. We could say 4.
Yeah, exactly. You'd estimate 4. And your actual would be 4.14. Good enough. You can read that spectrum. You can look, and by the combination of seeing a septet at about 4 parts per million, you'd say, oh, that's an isopropyl group with something electronegative on it. That's really, really useful. And the good news is you only have to keep one number in your head, and then you can go ahead and you can build out the other numbers that you need.
Dr. Nowick, I have a small question.
Sure.
So when you increase the, I guess the carbon chain, then you would also go towards more downfield, which means deshielded. And I guess I was kind of like, I don't know if it's not intuitive for me, but wouldn't the increase in carbon helps? Is it kind of the electron spreading around a bit more?
When you say increase the carbon chain, do you mean from ethyl to propyl to butyl?
Isopropyl, yeah.
Oh, you mean increase the branching.
Yes.
Yeah, so I think one way to think about it is, I mean, you could think of it probably in terms of the carbon being more electronegative than the hydrogens is probably a simple way of putting it. There's also a steric element that's involved, but I think you could just probably think of it as the carbon is more electronegative than the hydrogens is probably where I would take that.
Thank you.
You're welcome. All right, let me give you 2 numbers. So for some reason, I always think about either methyl groups or methylene groups, and it sort of depends on the context. But again, with that 0.4 difference, it doesn't really much matter what you choose to keep in your head. So for example, for an ether, I don't know, for some reason, probably because I've just seen too much diethyl ether in my sample. For an ether, I'd probably keep in mind about 3.6. And for an ester, because I've probably seen too much ethyl acetate in my samples, I would probably keep in mind about 4.1. Why do I do this for a methylene rather than a methyl? Again, it's just my habit. If you wanted to keep the number of a methyl ester and say, okay, a methyl ester is going to be about 3.7, or a methyl ether is going to be about 3.2, that's fine as well. You're going to get to the same place. I think the other reason why I keep the numbers here for methylenes in my head is they're very common and they sort of stand out because often you'll see a quartet or a triplet for spin or a doublet for spin-spin coupling, whereas singlets ironically, singlets are a little easier to miss. So if you get a methyl singlet, it's almost easier to overlook it than it is to overlook a doublet or a triplet. All right. In adding to our calibration, I want us to pay attention to beta substitution. Of electron withdrawing groups. And the reason is that it's enough to make a difference. Basically, you've got the inductive effect pulling electron density away. So if you've got X, carbon, carbon, hydrogen, where X is an electron withdrawing group, and that electron withdrawing group could be a halogen, a nitrogen, oxygen, carbonyl. The effect of a beta group in general is enough to pick up, let's say 0.2 to 0.5 ppm more downfield. So in other words, if you look at, say, ethanol, CH3CH2OH, the methyl group in ethanol is not a plain vanilla methyl group. It's not at 0.9 ppm. It's going to be a little bit further downfield, somewhere in the middle over here. And in fact, it's going to be at about 1.2 ppm. In other words, I'd say we can think 0.9 plus 0.3 is getting us to roughly where we're getting. Thoughts or questions at this point?
I have a quick question. So you said that for the ester, for something like ethyl acetate, you would see the methylene at 4.1. And I also noticed that the methyl at the very end, that would be like around 1 maybe, if I remember correctly. Is that from the beta substitution?
Yeah, that's exactly, probably a little further, probably more like ethanol, probably 1.1 or 1.2. But yeah, that would be from the beta substitution. And then that brings us to one more number to keep in your head. And that is that a methyl group next to a carbonyl is about 2 ppm. And what's nice about that, it might be a little closer to 2.1 ppm. I'm going to urge you to keep like one number in your head. So this could be acetone, it could be ethyl acetate, it could be almost any methyl ketone. I'm going to urge you to keep one number in your head. If you can keep more than one number in your head, great. But I like to lump things together. And if we're lumping, the other thing that I'll lump is a methyl group on an aromatic ring. And I'll also lump that at about 2 parts per million. We'll talk about ring current in just a second when we get to benzene. But, toluene, basically, you feel the ring current. And again, I come down to the fact that having that relationship of 0.4 ppm to bring us to a methylene, and 5/10 of a methylene of a ppm more, so 0.9 or 1 more, allows us to bootstrap ourselves so that we could immediately go ahead and say, okay, here's ethyl benzene or here's isopropyl benzene at somewhere around 2.5 or 2.4 and somewhere around 3 parts per million. So this is an example of how you can bootstrap yourself along, and why I'll say if you can only keep one number in your head, you don't need that many. I'll take one more example, and I'll take the example of a methyl group on a double bond. So in other words, this is what we would call a benzylic methyl or benzylic position. I'll just say benzylic position. And here, just to use the language that we often use as organic chemists, I'll say a methyl group alpha to a carbonyl. And here we'll say an allylic methyl. Or I'll say allylic position, since we're trying to be sort of inclusive in our language. And again, if you can only keep one digit in your head, lump it with the others. Put it as about 2 parts per million. If you can go ahead and keep a little more information in your head, I'd say calibrate, it's going to be maybe more like 1.7 instead of 2. But again, if you can't keep that level of detail in your head, knowing it's not going to be at 0.9 ppm, that methyl group is going to be about a part per million downfield of where it would otherwise be, is very, very useful. So some people say a little bit of knowledge is a dangerous thing, but I'd say a little bit of knowledge is a powerful thing. And we now have a little bit of knowledge just with a few numbers in our head. So let me write this molecule here. Let me write ethyl pentanoate up on the screen, up on the board here. And take a moment to think about where the various protons should appear at. What would you expect the chemical shifts of each type of proton in the molecule to appear at? So, somebody, where would we expect this methyl group to appear?
About 0.9.
About 0.9 ppm. Why?
It's basically a methyl, like without any other effects.
Very good. Somebody else, where would this methylene group appear?
About 1.3.
About 1.3. Why?
Because it doesn't have any electronegative atoms attached to it.
Doesn't have any electronegative atoms attached. It's not beta to an electron withdrawing group. Good. Somebody else, what about this methylene group?
I would still think it's, I thought that 1.3 was a little too high. I would maybe give that to that one that you're pointing at.
1.3 to this one.
Yeah, maybe.
Maybe. What other people think? Somebody who hasn't spoken up.
I think that could be 1.5.
1.5. Ah, we have a little bit of a controversy here. Why 1.5?
Because I think it's closer, a little bit closer to the carbonyl. And
It is closer to the carbonyl. What would we call its relationship to the carbonyl group?
gamma.
Pardon?
Beta.
Beta. Yeah. So all right. So by show of hands, who thinks 1.3? And who thinks 1.5? All right, well, 1.5 wins, but I'm hoping that we can have 100% voter turnout for our next election, and everyone is entitled to vote in this classroom. So, okay, so 1.5 is the winner by a majority, although not unanimity. How about for this methylene group?
I put that as 2.5.
2.5. And how do we get 2.5?
I forgot, but the alpha carbon after the carbonyl is around 2, I guess, and then binding to another carbon, I added around 0.4.
About 0.4. So yeah, that's a good estimate. So it is to verbalize it, methylene group alpha to carbonyl. And just to go ahead and put a finer point on this one, it's a methylene group beta to a carbonyl. All right. What about this methylene group over here?
About 4.
About 4 ppm. Why?
Because it's a methylene right next to like an ester.
Methylene group next to an ester. And I think I said 4.1 if we want to add another decimal place. 4 is fine. What about our methyl group over here?
About 1.
1. Can we go a little further on that? Because 1 is kind of right close to a vanilla methyl group. Can we give it another, can we characterize that, or how do we describe this methyl group here?
1.2 around.
1.2, and can we verbalize what the reason for it being 1.2 is?
Do we consider alpha beta too?
So this is alpha to an oxygen. And this would be what?
Beta to an oxygen.
Beta to an oxygen. All right, let's see how we did. And I'll share my screen on this handout. And so, oops, here's the spectrum. And if we look, we have about 0.9. And that's going to correspond to this methyl group. And then we have, let's just go with the easy stuff here. We have about 1.3. That's going to correspond to this methyl group. And we have about 4.1. By the way, make sure you can read analog. It's nice to have printouts, but you should be able to read a scale. All right, so here we have 2.3, and that corresponds to this methylene group. That's alpha to the carbonyl. We've got about 1.6 over here. That corresponds to the methylene group. That's beta to the carbonyl. We have about 1.4 over here. That corresponds to the methylene group. That's gamma to the carbonyl. So in other words, that little bit of knowledge that we have is very good for getting us to a point where we can pick out what the spectrum should look like. If we're off by a couple of tenths of a ppm, it's no big deal, but we know how to read the spectrum. And if you're good at internalizing this, you can self-correct. And if you draw a structure that doesn't make sense, you can fix it. Now, I'm going to launch Chemdraw here. I want to show you very briefly. This is a useful tool. As I said, having knowledge in your head, having that intuition, that calibration, nothing can replace it. That's the ability to read, but being able to get a little bit of help can help you along. And I encourage you to use available tools like this. So, and I also want to show you how they work, because now you have all the knowledge to understand how Chemdraw, when it gives you, predicts the spectrum, or at least when it predicts the chemical shifts for a spectrum, how it works. So here's ethyl propanoate, ethyl pentanoate. Here we go ahead and let's see, predict our chemical shifts. And I guess I need a different window here. So I'm going to share the window that just popped up. And here's the window that popped up, and it gives you the estimates of the spectrum, which looks very much like the actual spectrum. Is my screen big enough here? James, do I need to make this bigger?
Were you able to zoom in at all?
Yeah, I think so. Yeah, okay. Does that help?
Can you change the, okay, yes, that did help.
All right. So you notice, for example, on the methylene at 1.37, well, actually, let's start with yeah, let's start with the methylene at 1.75. It says, oh, it's a methylene. We'll call that 1.37. It's beta to a carbonyl. We'll add on 0.35, and then it makes a couple of other corrections for that. And that's very, very useful. For the methyl group at 1.07, it says a plain vanilla methyl group would be at 0.86. It's beta to an ester group, we add on 0.44. So it's doing the exact same thing with a few other corrections that really go beyond the scope of what we need to do. But notice all of those are down at sort of the 10th place, usually even the 100th place. And that is a tool that can help you. All right. I want to show you something very, very quickly. And actually, well, let me draw it on the screen. I think this is the next point, although my point is not really on chemical shifts in this example. I'm going to draw 3-methyl 2-pentanone over here. And we can apply the same sorts of skills that we did before and say, okay, a methyl group that's next to a ketone is going to be about 2.1. A plain vanilla methyl group that's far away is about 0.9. A methyl group that's beta to a ketone is going to be, let's just say 1.2 or 1.1, somewhere around there. And a methylene group that's beta to a ketone is going to be somewhere around 1.6. So these would be my estimates. I'll go with 1.1. I'll say we're adding 0.2 here. You could say 1.7. And that's a great estimate. This is what Chemdraw is going to give you. And I know because I just did it last night. Let me show you the actual spectrum and get us to the point of this example. And that's the last page of our handout here. All right. So we look at this spectrum, and now we can even start to recognize some patterns. So for example, it's very easy to say, okay, look, we have a singlet at 2.1. That's where we'd expect that methyl group, and it's a singlet. We have a triplet at 0.9, and that's where we'd expect that triplet. We have a doublet at 1.1, and that's where we'd expect that doublet. We have a multiplet. It looks like a sextet at 2.4 or 2.5, and looks like it's about halfway. I'll call it 2.5, and that's going to be our methane. And oh, I didn't estimate our methane on the whiteboard, but I would have estimated it at 2.5. And there's our methane group, or maybe I would have estimated it at 2.6 on the whiteboard. And now we come down to these two peaks, one of them at 1.4 and one of them at 1.7. What's going on here?
Are they diastereotopic?
Yes, and that is the point that I want to bring us to. These here are diastereotopic protons. In other words, in our chain, whether I draw it or not, we have a stereocenter. Even if the molecule is racemic, which I can guarantee you here, it is racemic, we have a stereocenter. One of those hydrogens is on the same quote unquote side as the methyl. One of them is on the opposite quote unquote side. They have a different relationship to that methyl group, whether I've drawn it as a stereocenter or not. And so these two protons are diastereotopic. That means they experience slightly different environments. Diastereotopic protons are not, and we'll get into this in our next lecture, not chemically equivalent. They often will appear at different positions. And although I'm not going to get into it right now, and they split each other. And we'll get into the coupling patterns later on. So I know we've run a little bit over, and I just want to finish with maybe a couple of more little facts that will really take us, I think, to completion over here in terms of our discussion of chemical shift. So alcohols and in general protons on OH groups occur at highly variable position, depending on whether they're alcohols, phenols, or carboxylic acids, about 1 to 5 ppm, about 4 to 7 ppm, and about 10 to 13 ppm, often broad or not seen. Due to hydrogen bonding and particularly exchange with water that's in the sample. If I want to make my carboxylic acid sharp or sharper, I will usually run it in DMSO D6. Because in DMSO D6, it's not going to exchange to water and it will hydrogen bond very firmly to the DMSO. Hydrogens on a benzene. For benzene itself, it's about 7.3 ppm. And in general, for an aryl hydrogen, it's going to be somewhere around 7 to 8, although that can go almost anywhere from 6 to 9, depending on how electron rich or how electron poor the aromatic is. The traditional explanation of why the protons are so downfield is due to ring current. And you can think of this in a classical model where you apply a B naught. You've got your electrons, your cloud of electrons, and the cloud of electrons basically sets up a ring current, a flow of electrons, and that ring current opposes the applied magnetic field through the ring, much like you've learned for physics of a solenoid, and the flux lines come around outside of the solenoid. And so this proton here ends up being de-shielded because it feels a stronger applied magnetic field. Feels a stronger field. And that is at least the traditional explanation. We can use a similar argument for alkene hydrogens. And that gets us to about 5 to 6 ppm as a typical alkene, although again, they can vary in chemical shift a little bit. And that argument also, plus the electron withdrawing oxygen, can be applied to aldehydes, and that gets us typically to about 9 to 10 ppm. So the one sort of oddball, here, I think for me, I'm a lumper. I like to lump ideas together. So I lump the alkenes, the arenes, and the aldehydes together. The one that's sort of initially counterintuitive is acetylenes. And those hydrogens, which you're going to see in the homework very soon, are about 2.5 ppm. And your first thought might be, wait a second, this hydrogen, it's on a triple bond, that should be like a double bond. And if you want to think about it in the same sense as a ring current, you can. Here's your applied magnetic field. You've got this cloud of electrons, and that cloud of electrons generates a ring current. And that ring current opposes the applied magnetic field. And by the right-hand rule now, you're seeing a shielding of that hydrogen. So instead of being like an alkene, where you end up having a sort of ring current that is like benzene, you can think of it as having a ring current where now your flux lines are basically protecting that hydrogen from the applied magnetic field. All right, last thing I want to say, because I know I've run way over. I think analog. I read a spectrum and I read it analog. And so in my analog mind, I keep this in mind, that we sort of start over here at the upfield region of the spectrum. And in my kind of analog mind, here are our methyls, here are our methylenes, here are our methynes. This region over here, somewhere right around 2 and a little bit further, I think of as allylic, benzylic, and alpha to carbonyl. Moving a little further downfield, over sort of here, I think of CHX, CHO. Moving further downfield, I think alkene. I think arene over here. And finally, aldehyde. And that sort of ability to read ends up getting you pretty far. If you can look at a spectrum, look at the regions, and start to read it in like this, you're in pretty good shape.